It was sent on today in the morning.
Yeah, but I only have an email saying that I was like. Oh. So I guess we can start, or
Are we live or?
we can start, yeah? Very good. Okay, so welcome everyone to our PCS seminar. I guess it's the second or the third one, which is run in this hopefully again on-site or hybrid now mode. And I hope that we will see each other here more often, more frequently in the future. It's a great pleasure to have today Boris Altshuler with us, who will give a talk on many-body localization in the solid 1D Hubbard models with infinite on-site repulsion. And I guess most of you know Boris very well, who is also since quite some time serving as a member of the scientific advisory board for our center, for which we are very grateful to him. And he's also did quite some amount of joint research with members of our center. And for those of you who are less familiar with his CV, let me just very briefly mention that he did his PhD in 1979 in then Leningrad at the Leningrad Institute for Nuclear Physics, finishing before that his physics studies at the Leningrad State University. And he then moved at the first possibility, I would say so, when the old Soviet Union was breaking apart, he moved to the United States, where he had held several positions, and I will not list them all. Right now, he's at Columbia University, and he has a number of awards: the Hewlett-Packard Physics Prize, the Humboldt Research Award, the Oliver Buckley Prize of the American Physical Society, the Dirac Medal of the University of New South Wales. And however, most important I want to say is, of course, his scientific achievements. There are many, and I just went to Google Scholar and I typed in Boris Altshuler and printed the first page. And there you find a number of interesting papers, highly cited papers with Aronov and Patrick Lee and others. But probably you all know him, or the world now knows you most for this work, which is seminal work with Basco and Alener on many-body localization from 2006, which received more than 2,000 citations, according to Google Scholar. So it's a great pleasure to have you with us, and we are looking forward to your lecture. Let's welcome Boris.
Thank you, Sergey. It's a great pleasure to be here. And I'm not kind of accidental guest here. I have been here many times, and dared to put your center as one of my affiliations. And I gave already several talks here, including several talks about many-body localization. And today I decided to present a rather recent paper, which we made with my colleagues at Russian Quantum Center, Murat Bakhladinov, Denis Kurlov, and Zhora Shlapnikov, and also Matvienko, Fedorov, and Volodya Gritsov. There is a very recent paper which is still not fully published yet. And especially I want to emphasize collaboration with Murot and Denis, and I strongly recommend you this very bright young guys. So it will be about many-body localization still, but the problem that we have is that although the whole story was planned and constructed for real many-body problems, and there are people dealing with certain spin chains, but a lot of interesting features, a lot of interesting questions have not been yet applied to real systems because life is often too complicated, and many people, including myself, started to think about some kind of matrix problems which mimic these features of many-body localization, but it looks like there is a model which is many-body and which is very simple. Sometimes on the first sight it looks even too simple to carry interesting features, but I believe it can make a good laboratory for studying effects of many-body localization because it doesn't carry certain complications than other models. And I'm thinking about what is known as Hubbard model with infinite on-site repulsion, and what we try to do is to take into account the disorder in this model. So I don't think I need to speak too much about Hubbard model. Let's say for Fermi Hubbard, we have the possibility for our particles to jump between neighboring sites, and the first term is responsible for that. And there is another term which makes the system pay some energy for having two of these particles on the same side. And since we are speaking about fermions, these particles should have, of course, opposite spin because each side is supposed to have only one energy level to host a particle, and we don't allow, and we have to pay price U for putting particle with spin up and particle with spin down on one side. And although in high dimensions this Hubbard model is pretty complicated, in 1D it is integrable, and well, I forgot to tell that the Hilbert space of this model corresponds to each side having four possibilities. It can be empty, it can have spin up, it can have spin down, and it can be double occupied. And you can estimate the dimension of this Hilbert space as 4 to the power L. So even if you have, let's say, 10 L is length of the chain, if you have only 10 sides, it becomes already million, more than a million, and it's not too easy to study it numerically by exact diagonalization. Nevertheless, as I told, this problem is exactly solvable, and there are zillions of papers devoted to it. The pioneering one was famous paper of Lieb and Wu, and also Shriram Shastri brought important contribution, and together with Emil, we also added our 5 topics to this story. but I'm not going to bother you with better answers today. I just want to mention that in principle, even at finite u, this problem can be integrated. Now, what I want to discuss is the case when this repulsion u is infinite, which means that we actually don't allow this double occupation. And because of that, our dimension gets reduced. It's a little bit less, only 3 to the L. And it's still exponentially large, but it's a little bit easier to deal with. But also, it is quite possible to understand a lot of details of these models, as I will try to explain you much further than you do for Hubbard with finite u. And another way of writing the Hamiltonian is not to write this interaction term, which is infinite at all, and instead to tell that we have something like a tie binding model and project it on the stage, on the space where where two particle occupation is forbidden. So P is projection. It vanishes at every case when we have both an up and down at the same side equal to 1. And as any projection, its square equals to itself. And this is our Hamiltonian to think about. And in spite of being simple, there is still a big literature on this problem where a lot of things were understood for this problem without disorder. And again, the main tool was better answers, and I'm not going to go further into details. Instead, I will try first to kind of qualitatively explain what are the states of this model, and then we will see how we can destroy this integrability and apply our ideas on many-body localization transition to this model. So let me specify. Let me have L length of our chain, N will be number of particles, and in my head, as condensed matter physicist, I assume that both of them are large, no, macroscopically large, but you will see that we cannot move numerically too far. So results that I will show you are limited by L of order 20. And for the problem to be interesting, of course, number of particles should be smaller than the length, so there are empty places. The number of empty places is equal to n minus L, and there will be n up particles with spin up and n down particles with spin down, so that the sum is equal to L. And what is also important is that from now on, I will assume that we have a periodic boundary condition, which means here we have J changing from 1 to L, and we have to tell something about C L plus 1, and it will be equal to annihilation operator at psi 1.
Sorry, n plus and the minus are separately preserved, right?
Yes, you will see that something more is present. Okay. So before moving further, let me introduce you something that is quite common for one-dimensional models, but here it's especially simple. And this thing is called spin charge separation. So you have, for example, a particle that is allowed to move from one side to another. But on equal footing, we can tell that it's our empty place, emptiness, is moving from right to left. And actually, what we can think about is that instead of discussing our spinful particles moving, we will discuss these spinless empty places moving along our chain. And if there is no disorder, then this motion of empty place from right to left is easy because there are same energies, and that's why it looks like this empty place can move like a free particle and behave like a fermion, because as you understand, two emptiness on one side is impossible, and that's why they cannot occupy two of these particles cannot occupy the same site, and this is the only thing is needed in one dimension to call these particles fermions.
Sorry, Jack, may I ask you one question? If you put the on-site energy for a single particle.
Yeah, so yeah, we can put on-site energy, but if on-site energies are the same,
Yes.
then it's still not change potential energy when you move your energy.
But I just confused the same energy between the empty and solid particle.
Right. So if we consider energy of the system of one particle on two sides, it will be the same energy.
Yes.
Just because we don't include any disorder. But I will include disorder very soon, so don't worry. Okay, and let me call this particle Holland. It's a pretty common thing in this field to discuss particles that carry, if you want, it carries charge, which is opposite to the charge of a real particle, but does not carry spin. And the question you can ask me what you are speaking about, you just explain us that this system is a system of free columns, free fermions, and why we need to even to worry about it, we know how to deal with Fermi gas. And the point is that it's not exactly the gas of non-interacting particles. It's a little bit trickier, and let me explain why. So we still don't have disorder, and suppose we start with the situation when we have, just for simplicity, one empty place and three particles, up, down, and down. And I want to see how this empty place is moving along my chain. So it made one step clockwise, and I'm keeping track of what happened with this spin. So this, as a result, this spin up moved into a right up corner. Then there is second step where our empty place, our column, is in low right corner, and then there is a third step when it is on lower left corner, and you can check everything is on the screen that after 4 steps this particle returned to the same place as it was. But if it would be completely free particle free fermion, we would say that wave function should be the same in this case and in this case. But you can see that we actually did not return to the same many-body original state, because beforehand our spin down particle was on the lower right corner, and now it is in a higher right corner. So what happens is that when our Holland goes around the loop, around the chain, it does not bring your system to the same state.
But it has the same energy, so for the moment.
Yes. And this is important.
Right.
But this doesn't need even a U, right? This is true even for.
U is equal to infinity.
No, but you don't need U to. You can get the same result also for 0 U.
No,
Why?
because for 0 U, one of the possibilities is that in the intermediate state,
Yes,
two particles will be in one.
Yes.
So you can change without moving the empty place.
Yeah,
You can change this up and down.
Well, there are other outcomes, but this is still one possible outcome even for 0 U.
Yes, but as I told, 0 U is another story. Then your particles will behave as free fermions. But here they don't. You will see that they don't at all.
Sure, but what you want to say, probably, is that that's the only outcome which you have if you want to rotate.
Yes. So what I need to do is to make another 4 steps, and again, Holland return to the same place, but my spin down is in the lower left corner. And then again, and finally, you see, I got back.
This scenario, do you also consider the hopping?
Excuse me?
And is a hopping term is considered here?
No, hopping allows, now I'm just asking, you see, if it would be just no spins, no marks here, a particle goes around, and what I need to demand is that wave function at state site L+1 and L should be equal to each other, right? So my quantization would be what you read in a textbook, that momentum of the particle equals to pi divided by length, right? But here I cannot tell that the wave functions of this state is wave function of this state. It has the same energy, but not necessarily the same wave function.
If you consider in terms of the chemotonic, if you consider the first term, which has the hopping key,
Yes.
then the hopping
Allows you each of these steps. If there would be no hopping, we will put our particles where they are, and they will stay there forever.
My question is I guess all of these configurations have the same energy.
Yes.
So if I consider the hopping term in the Hamiltonian, which has T times
Consider a particle in a crystal. At each side, it has the same energy. What we're then telling you is that we have tight-binding model, and in tight-binding model, the eigenstates are plane waves, which is linear combination of states at different sides with some phase path, which is Bloch theory. And at the end of the day, if we want to understand what are allowed wave values of this quasi-momentum, we tell that wave function at has to obey boundary conditions, and then it gives us the quantization rule. So what I want to tell is that wave function of this Holland does not obey usual boundary conditions. Is it clear?
So does it mean it has some fractional statistics?
Yeah, in a sense, it's a little bit simpler than that. I will explain everything. Nothing
That's a monodromy, right?
What?
I mean, it's like a monodromy problem.
If you want.
Yeah, okay. Yeah.
Okay, so basically what happens is that from this sequence, you get to this sequence and you get to this sequence, and only in the fourth attempt, you get back to the originals. So Holland has to make 3 full rotations for the system to return to the originals for this particular case. And now we can use this fact in order to understand what are the wave functions of the Hollands. Indeed, they are almost like free particles. So they are characterized by quasi-momenta. There are a system of Hollands has a set of L-1 this quasi-momenta that characterizes it. But these quasi-momenta are quantized according to this law. We have to make 3 revolutions around the system, and this product should be equal to 2 pi times an integer, and as a result, can you see me here? As a result, ki times L divided by 2 pi is either integer, as it would be for simple Fermi gas, or integer plus 1/3, or integer plus 2/3. Yeah.
Where are the number 3 indeed? Yeah.
Well, okay, yeah, that's right. Is it 3 just for 4 sides, different for larger sides?
1, 2, 3.
Yeah, question is whether this is universal for any.
No. Just I will generalize.
Okay.
This is exactly for this particular. And this is the question of what all this means. I will try to explain, but what I want to tell is that there is a possibility to consider these Hollands as if inside the loop there is some magnetic flux, and this flux is equal to either 1/3 or 2/3 or 0 of flux quanta, so that if it would be like this, then we will have also quantization rules either of this type or this type or this. So the question is where this non-integer flux is coming from, and what is its physical meaning.
Just to be sure that I'm understanding, in the right plot, essentially there are no particles anymore, and you replace the particle with the magnetic flux. Am I right?
Yes.
Okay.
Yes. So what is the physical meaning of this magnetic flux? And what I want to do to introduce some words which I'm not sure it is completely sorry. What happened? Yeah, so maybe when it is fixed, any more questions? Anything that you would like to?
Just a short question. Yeah, is the model in the example to consider the up-down of operation?
No, right now I'm considering any configuration.
Yes, yeah. But
because you will see, and maybe this I can tell me without showing the picture, is that there is something which is conserved whatever you are doing with this motion of Hollands. And this something is what I call a pattern. So pattern is the same in
No, what I mean is that if you consider this the four sides
yes.
and the ring and the single colon, and if other particles are spin off,
Yeah.
no spin off,
Yes.
then you know the single
Then of course,
rotational
yeah,
part
no, no.
that gives
If all particles are spin out, it will be free gas.
no such the three tone.
Correct.
I mean,
What?
yes, the
Yeah,
spin
there
factor.
is no magnetic flux in the case.
So I
The
mean,
question is, what are allowed values of this magnetic flux on? It got scared. Okay, so definition. I don't know whether it's acceptable in mathematical literature, but let me consider sequences. I number my sides, and sequence would be up, down, up, or up, up, down. And it turns out that what the motion of a column does, it basically makes a cyclical transmutation of this sequence. And what I call pattern will be a given sequence together with all of its cyclical permutation. And cyclical permutation is motion of the pattern around the ring. And as we discussed, there is L minus N quasi-momenta. No, it doesn't want to. Now it looks.
Not sure.
No. And now it's important to emphasize again that each of the spin sequence has the same potential energy without disorder, even for different patterns, but surely for the same pattern. And what I can speak about is what I call pseudocrystal. So this is a crystal in a space of the sequences. So all this corresponds to the same pattern, which is conserved, whatever columns are doing. But there are distinct states which have the same energies. And system, in principle, can move by rotating a column around the ring. It can move from one sequence to another, and so on.
Sorry, I mean, so far this notion of pattern, I think, is highly, let's say, tailored to the case in which you have a single column, because
No. Pattern sequence is what you have. What you have if you take all emptiness out. If you have, like, let's say, I will give you some example and we can discuss it. Just give me 2 more minutes.
I see. Yeah.
So now, what you have if you have distinct states with the same energy and possibility to move from one state to another, you again have Bloch's theory, and your state of the system is a Bloch wave, and this pattern is characterized by its quasi-moment. So, yeah.
Can I ask? So if you have more than 4 sides, or
I will go to arbitrary number of sides.
kind of like a rotation of the entire pattern of your ups and downs spin electrons, right?
Yes. It's no, each of them, they can only move like wagons in a train.
Exactly.
They cannot go through each other.
Exactly.
But this train can go around the ring.
Is this quasi momentum defined by some kind of translation operation of the whole?
Yes, so column goes around and you get from here to here. And then you can get from here to here. And at the end of the day, you can have a state with this sequence state with this sequence times e to the I phi times something and plus this sequence e to the 2 pi 2 I phi and so on.
So like, I guess, I mean, some kind of translation of hormone is defined by basically starting with the nearest neighbor halving of the function at the spin, right?
Yes.
So how is this hormone's translation operation related to?
Yeah, because hopping between this sequence and this sequence is in our previous picture was exactly this transition, let's say from here to here. Column does this, and this gives us matrix element for getting from here.
Also, that one cycle makes the whole of the translation of symmetry.
Yes, yes. Yes. So this quasi-momentum of the pattern is something that characterizes the system. And because all of the spin sequences have the same potential energy, this quasi-momentum is conserved as quasi-momentum of a simple quantum particle is conserved in a ordinary crystal or in an ordinary periodic potential. Now, you wanted arbitrary number of sites. And the question is how many non-trivial sequences are there in the given pattern. And because if there is ns sequences in a given pattern, our quantization would be 2 pi times integer divided by ns, and this integer will go from 0 to ns minus 1 because ns and 0 is equal integer. And in our simple example of one hole and 3 particles, we have 3 sequences which are non-equivalent to each other, and that's why we have ns equal to 3. But in general, it can be.
Sorry, just one second. By pattern, you mean what? What do you mean by pattern? It's just the setup where how many spin up and spin downs you have? Is that what you mean?
No,
or what patterns?
Okay,
No,
so,
sequence and pattern.
I think I somehow.
In the example, maybe yes. Here. So what is a pattern? So the sequences are these 3 different.
So this is what I would call nail pattern.
But then,
Okay.
We need help.
Oh,
Okay.
this is.
It's like this: up, down, up, down, up, down, and so on. Now, what is ns? For nail pattern, ns will be down, up, down, and so on. These are non-equivalent. But next cyclic permutation will bring you back to the origin. So for nail pattern, ns equals to 2.
Yes, but by pattern, that's again my question. By pattern, you mean basically the setup, how many spin ups and spin downs you have in your.
Non-trivial. No. Non-trivial permutation. For example, let me give you another example. I have all the spins up. And
I see a sequence together with all of its cyclical
yeah,
permutations.
and then
Thank you. Thank you. I think I got the answer.
no, let me finish because maybe other people didn't. And then I start making cyclical permutation, and I need as many as n of them in order to come back.
So number of distinct pattern is equal to the number of quasi-momentum possible, right?
Excuse me, can you repeat?
The number of distinct pattern is equal to the number of quasi-momentum possible, right?
Yes. Number of possible quasi-momenta is equal to ns.
No.
As number of states in a crystal. You can tell that as a Hilbert space, you can take this state, and this state, and then your eigenstates will be linear combinations, but number of non-trivial will be equal to this. So we have this.
What here? It's the permutation. I think
Yeah.
this black thing.
You will give it to me.
Yes.
Okay. So now I had some problems here, as you can see, but we will manage to understand. So what we found is that each pattern, and I hope you understand what I call by pattern now, generates a family of many body states, which are characterized by the set of Holland quasi-momenta and by quasi-momenta of the pattern itself. So this is symbolic in the Dirac notation property of eigenstate. You have plane waves of the Hollands. You have also plane wave of the pattern and pattern itself. So if you start with naive, not only there will be only two values of phi, but you will never get to this point. Your system will stay with this. If you will have periodicity phi of your sequence of spins, then NS will be equal. Now, second, this quantization is quasi-periodic. And important thing is that if you calculate the energy, then this energy is the same as the energy of the tight binding model. So it will be, Jackie, you want to see something?
Sorry.
No, it's okay. It's okay. So it's the formula you would write for tight binding model for free particles.
Sorry, you have to open the journal.
Yeah. Okay.
Yeah. Oh.
It's a long way back to normality after pandemics.
Yeah.
And Zoom doesn't make it easier.
But again, I answer some questions meanwhile.
So can you have scattering of these Hollands?
No, it's the same as free fermions. They don't interact with each other.
So are you saying these are exact eigenstates
Yes,
of the TJ model?
T0 model with J equals 0. Because TJ is different thing. If you have, let's say, two particles, two spins, integrate, they interact. If I put a hole between them, you lose energy of the interaction. But here, since there is no J, you get it for free.
What is the?
So can you get this from Bethanzats too, as some limit of Bethanzats?
Yes, I can tell you how what is the answer for the Bethanzats answer. But first, I want to emphasize that this is, if you forget about quantization, if you forget about this phi, then this is energy over Fermi gas. So energy itself depends only on Ki, but you cannot tell that energy is independent on phi because through Ki is it depends on phi, and it of course doesn't depend on pattern itself. Yeah.
So it is similar to the single particle or tight binding model. So there is some so like what is the hopping here? Like we have 2e cos cosine k.
No. Hopping for holons is original hopping. I wrote character t. I mean, it would take me too long to go back, but there was yeah. So this t in our calculation we put it equal to 1, but this provides hopping between sides, and then I get decent tight binding quantity. The only difference is quantization, but quantization is itself this flux is kind of, if you want, dynamical variable, and it's yet one more conservation law. So all these cases are conserved, but also this phi is conserved, and the pattern itself is conserved. Now, how the Bethanzats answer looks? Instead of phi and pattern, you have a set of magnetic rapidities together with charge quasi-momentum. And in the quantization condition, you get some of these magnetic rapidity. And the rest of them are responsible for this pattern.
The expression for energy, I think, is the same in Bethanzats.
No, absolutely. This I'm repeating again and again. The equation for energy is what you get from the text. The difference from the free gas is this, yeah, this quantization. But as a result, I mean, this depends on what is our pattern, and this depends on phi. So everything, in a sense, the spectrum is quite complicated if you mix states of different pattern and different pattern. Okay, now what happens if you have potential disorder? So what we had beforehand is this T0 zero states instead of J, and what I will add on each side, I will add certain random energy epsilon J, depending on the occupation. So if that should be, of course, J and sigma and sum over sigma, but we understand that in our model n can be either 0 or 1, and it's either sigma up is there or sigma down is there, or none of them. And what you can, if you want something concrete, you can think in terms of the Anderson model, where these energies are independent from each other and assumed to be have uniform distribution between minus W and double. And then what turns out, and I will try to explain in a second why. It turns out that we will have the single particle problem with the same quasi-periodic boundary condition, and this single particle problem is problem of Anderson localization. And I just want to remind what is problem of Anderson localization. Original, it is a quantum particle which is subject to some random potential. This story is started in middle of 50, and this is kind of starting point for a lot of more complicated physical problems. And what we know now is that for continuous limit or for tight binding model with disorder, if we're dealing with three-dimensional system, or if you're a mathematician and think about number of dimensions which is even bigger, then we have transition. So there can be extended states and localized states, while in low dimensions, namely in 1 and 2, all states are localized, regardless to what disorder is. And in particular, in our case, we also, in the presence of disorder, deal with the localized states. So we have localized one particle states. I will call them alpha. And this alpha, the number of states is equal to the number of sites, of course. States only can move and change, but their number is not changing. And the occupation numbers of the states, so some of these localized states of columns are occupied, some are empty, columns are spinless, and the total number of these columns is still n minus L number of 80 places in our lecture. And it turns out that many body states, instead of being characterized by set of the quasi-momental columns and the quasi-momentum of the pattern and pattern itself, will be localized by the set of these occupation numbers. You can catch me and tell that there are L of them, and those are L minus N, but the set of alphas for which N equals to 1 is also L minus N. So it's basically the same number of quantum numbers, which is again conserved. And pattern again is conserved. And what is also important, that in spite of disorder, the quasi-momentum is also of the pattern is also a conserved quantum number.
This is because epsilon j is independent on sigma, right?
Yeah, I will explain. Just say. So in my language, it means that even in the presence of the disorder, the system remains integrable, because it has many body states are characterized by the macroscopically large number of quantum numbers. Basically the same number as we had for systems without disorder. Only, I repeat, instead of the quasi-momentum of the columns, we have the instead of plane waves, we have localized states.
Sorry, but before KI was, they were functional.
mean, non-trivial or trivial functions of the phi. Now this and alpha.
No,
For the eigenstates, here are just the state. You say you are just.
yeah, so
Okay.
let's speak again about Anderson problem. So for Anderson problem with finite size system, you still have to worry about the boundary condition in order to everything to be fixed. So you have Schrödinger equation and you solve it with a given boundary condition. Now, if you have localized states, which is localized somewhere inside, then effect of boundary condition is actually exponentially weak because it's only tails of the wave function that are filling the boundary conditions. But it's not zero. So in principle, when you change boundary conditions, you change your wave function a little bit and you change your energy. And that's why what you have still, if you want, splitting of your spectrum into states with different boundary conditions. Although this splitting can be much weaker than in equilibrium. But the main conclusion that I want to emphasize is that in spite of the disorder, system remains integral.
Sorry, what I'm still failing to understand is that these states, that you call many body states, are the eigenstates, or they are just.
No, these are many body eigenstates. Because all these things are conserved. If you fix set of n alphas which are occupied, and you went for lunch, you come back, and they are still occupied. This is, they are integrals of motion. It's like you have free particle, its momentum is conserved. It's exactly the same stuff.
But I'm confused because there is the open term. So an alpha, I mean,
Coping terms.
so
Once more, let's consider one particle in a periodic potential. You have Bloch wave.
Right.
You add disorder. Instead of Bloch waves, you get localized. Right? You put many particles which don't interact with each other. What happens is that some of these localized states are occupied, some of them are empty. But as long as they don't interact with each other, they remain either occupied or empty forever. So your occupation numbers are integrals of motion.
but wait, okay. I was confounding. Alpha is not the label J. It's a label for the single particle eigenstates. Okay, now I get it. Okay, sorry.
No, you still have to turn on your computer and actually compute these states. But,
Okay, sure.
but there is huge difference between one particle problem and one body problem.
Sure. Now I get it.
What about finite U? Because this is for infinite.
I don't know. I think all this, I will think about it a little bit later, but I don't know even how to take into account U, which is very large, but not zero. Because immediately you start to have exchanges and I mean, it's something to start doing because you can try to develop certain perturbation theory and nobody can do it better than you. But no, I mean, it is not something that is so much easy to do, although, as you can see, everything is on the table. All states, all wave functions are there, just calculate.
I mean, physically, one would think because it's repulsion, it's still going to be localized, even for any U. No,
no, they will be localized, but there will be processes which mix different occupations in different files. So the terms, extra terms that appear at finite U will create matrix elements between the states. So they will not be conserved quantities anymore. And now what you will need to do is to calculate these matrix elements and analyze this matrix from the point of view of whether it gives you many body transition or not, and so on.
It will be many body local.
Yes, yes. No, well, this is what I'm going to speak about if I have time, because I don't know. It's only 5.
It is 5, and I think we can still go on. It depends on you.
No, okay. No, I'm fresh, but people can have contact. So let me. I mean, you asked many questions, but you didn't ask me the question which I find interesting. Now, why? Why I told you that the quasi-momenta of columns are not conserved, and we have to deal with localized states, while the quasi-momenta of the pattern is conserved, and this is the case. And the answer is again that all of the spin sequences are characterized by the same potential energy, because it's random potential. You pay the same price for putting a particle with spin up on your side or particle with spin down. Mm-hmm. And that's why these guys are scattered and get localized, but our pseudocrystal is still perfect, and states in this pseudocrystal are still characterized by, still described by the block theory. Yeah.
So then, I mean, in practice, you can do the numerics in a given particle number set, right? Because your N alpha is conserved, right?
In a given particle number set.
Yes, but not only. You can make your calculation for a given pattern. You have to agree that you either start making calculation for this or something like 2 up, 2 down, 2 up, 2 down. You will get different results, but you don't have to mix it. And of course, to be efficient in numerics, you have to use all the symmetries, because it effectively reduces the size of the matrix that you have to diagonalize in there. Okay. Now, why I would why I have to deal with the what does it have to do with the problem of multi-body localization? In fact, let me go very quickly. In fact, when we're thinking about integrable system with large number of degrees of freedom, then we have, in classical case, separation of variables, and we have d integrals of motion. Our classical trajectories are on the tori. Each tori has dimension d and is determined by the set of d integrals of motion. And our energy shell has, for large d, much larger dimension, almost twice as large dimension. And then the generic problem is what happens if you add, if you perturb your integrable Hamiltonian by something that violates integrability, and how this violation will drive you from this integrability in some region of very weak violation of integrability to the situation where we can start thinking in terms of traditional statistical mechanics, things equipartition and all this. And let me try to be quick. So what I propose is to consider even classical problem in the space of the integrals of motion. And then if system is integrable, in this space, the state of our system is a point. So this tori corresponds to a point, and the energy shell is still a surface which has dimension equal to d minus 1. Now, what CAM tells you is that at least most of the trajectories at finite but very weak violation of integrability are still concentrated in certain region near the certain small region and are not smeared all over the energy shell. And when you go to the quantum situation, the only difference is that instead of continuous space, we have a lattice because normally our integrals of motion are quantized. As we saw in our case, all these momenta for finite system were quantized in the same as a result, what you can expect is that if violation of integrability is weak, your wave function, your eigenstate of this perturbed Hamiltonian will can be expanded into eigenstates of H0 and involve only a small number of terms, and still it will be not one number of terms because this perturbation provides certain transitions between sides of this lattice. And this lattice, for example, if you have the simplest integrable system, rectangular billiard, you have two components of the momenta, which are conserved classically. Energy shell is a kind of semicircle or circle, if you want, and you know how to quantize the momenta, so you will get this lattice, and then you will start thinking about perturbing this motion, adding some smooth potential, which will scatter your body. And in general, what you have, if mu are eigenstates of H0, which are integrable, then the H0 can be diagonalized, and perturbation has off-diagonal matrix elements, and in this lattice of states of integrable system, you have certain transitions, and to make long story short, you have these matrix elements, which is nothing but if you have transitions only between nearby states, you have something similar to the understanding. Okay, now let's come back. I hope I will finish in 5, maximum 10 minutes. As we discussed, in a case of potential disorder, we don't violate integrability. The system remains integrable, and we have all these conservation laws. And in order to violate this integrability, you can try to put another type of disorder. So this is potential disorder, but I want now to add random magnetic field. So in this case, the energy will depend on whether we put spin up or spin down, and it will be either plus HI and minus HI, and this thing also will be random. So, Emil, I don't know. I would love to, instead of this, include finite U as violation of integrability. But this seems to be much simpler from any point of view, and still promises to provide you some transition. And the point is that this supercrystal is not perfect anymore, because with this term, the energy depends on the sequence, and quasi-momentum is not conserved. And this is our H0. This is random field part of the Hamiltonian, which violates integrability. And what we can check is that between different states of the integrable system, we have the states, we have non-zero matrix. And indeed, what we expect, what we could expect, is the transition from states localized in this basis to states which are extended and maybe even ergodic in this basis.
So upon adding more disorder, you expect the system to become ergodic.
Yeah.
Because it's a qualitatively different design.
Yeah, because you get this matrix element.
Yeah.
Yeah. Yeah.
But why taking random?
Why? Because what else do you want?
Constant.
Constant
Or uniform.
Then again, energy will not depend on the segment. No, if energy doesn't depend on the segment, phi is integral of motion, and that's it.
Oh, that also means that if, instead of magnetic field, you add nearest neighbor interaction. You still have.
Yes, no,
So long as it doesn't depend on space.
yes, you can look, guys. You have extremely good computer equipment. If you want to, instead of this way of violating integrability, discuss something else, I'm with you. but this is what we did. And again, it's indeed kind of not intuitive that you start with something integrable, you add some magnetic field, and you violate integrability, but for a while it is many-body localized, but then it is maybe extended, and then later it can be localized again, but already in a different way. And another question is about ergodicity, whether there is transition between non-ergodic and ergodic. So I will show you our numerics, which Moral Mahabedinov did, and I think that it is pretty promising, but of course, some kind of extension and maybe refining these algorithms can be useful. So let me skip. If there is, there would be questions about what ergodicity is, I will answer. But what is important is that one of characteristics of system is so-called fractal dimensions. So I is here determining the states of integrable system or sites in our model of psi I is wave function. And if we consider this type of the entropy, if you want, or moment of participation ratio, as we used to call it before, then for Q equal exactly 1, normalization gives you 1, but for Q different from 1, you expect some kind of power-like behavior. If states are localized, then these powers are equal to 0, all of them. If states are extended so that psi square on each side is of order of 1 over n, because we have n sides. This would be n to the power q,
and minus q, I'm sorry. And you have n of these terms, so tau q will be equal to q minus 1. So for ergodic state, tau q is q minus 1. For localized, it's 0. And in general, you can consider this ratio. And when d is between 0 and 1, we're dealing with multifactor state. For one particle Anderson model, we have one transition from the localized states to extended states when we change disorder. And this is also transition from localized to ergodic. But in the very vicinity of the transition, we have these critical states which are multifactor. Now, this is what more or less follows from our calculations for the problem of disorder. This is here is potential disorder. Here is random magnetic field, and of course, large random magnetic field gives you localization even without potential disorder. If you have zero magnetic field, everything is localized, but very small magnetic field actually drives you into the extended states, and this is characterized by this fractal dimension d1, of course, in this finite system. So red means d1 equals to almost to 1, and the blue is somewhere between 0.1 and 0.2. Now, the last two graphs, this is d1 and d2, two fractal dimensions, and here, I think it was not a good idea, but it's my fault that I enforced everything to be plotted in terms of total disorder and this angle, so that angle theta equals 0 is only a random magnetic field, and here should be doubled, and here theta equal to pi over 2, only random disorder. So what is plot here is only random magnetic field, and you increase the disorder, and you can see that when field is weak, you have this fractal dimensions close to 1, and when field is large, it reduces and becomes much smaller. But what is really important is that curves for different system size seem to do something like crossing here. And this crossing usually means a phase transition. So you can expect that everything to the left is extended and everything to the right is localized. And there is also this Kuhlbach-Leiber divergency, which, if you will ask me questions, I will tell you its meaning. It is the definition where you study the ratio of the occupations of given site by two states which are neighbors on the energy scale. And it turns out that for extended states, not necessarily ergodic, it's equal to 2, and for localized state, it's very large because the states which are localized, usually two states close to energy, are very far in space, and that's why this ratio is always very big. So if psi alpha is large, then numerator is large and denominator is usually exponentially small. So this logarithm is large and you have 0. But when you start to approach the transition, you have very interesting phenomenon when states that are localized in the different places get hybridized. So instead of one state here and one state here, you have the bonding and anti-bonding state, and their psi squares are the same. And because of that, this quantity gets very quickly reduced, even when states are not really ergodic. And that's why for extended states, this Kyle divergency is 2 and it's close to 2. But as soon as you undergo the transition, then you have very quick increase. And again, there is something like crossing. And finally, this is what happens. As a function of the angle, so when you change the angle, you go from pure magnetic field at small angle to pure potential at a large angle. And you can see that here we have extended states and very close to pi over 2 when we have the we have this transition to the localized state. So the transition in terms of the angle happens actually at very weak external magnetic fields when this theta is very close to 0.5. So very weak magnetic field actually destroys the integrability and drives your system into extended state. That's basically all what I wanted to tell. And in a sense, this is story which is still under development. I think this problem is very promising as a laboratory of studying the subtle questions about many-body localization, and I strongly hope that some other group will join us in doing this competition. Thank you very much.
Can I ask a question?
Yes, first let us say just thank you, Boris, for this fantastic lecture and talk. And I hear some Zoomer, and I'm not sure who that is. Please identify yourself and ask the question.
Yes, thank you very much for a very interesting talk. And I wanted to ask a question. You show a plot where was localized and delocalized regime in WB plane.
Yeah.
And I have a question whether there is some power law dependence at small b, or what is the law of dependence of critical W on B at small b here? Is there some power law?
I showed you all the curves that we have. So you want a region of small b and this transition, right?
Yes, maybe there is some power law dependence or some fit of this dependence or something like that.
Yeah, I think you have to analyze better these curves, and I cannot answer that question.
Okay, I see. And maybe another question. I'm not a big specialist in numerics, and I just wonder why the L equal to 20 is the maximal which you take in your calculations.
Well, if you are very naive, you would tell that n equal to 20 is a million sites. So then you are dealing with million by million matrix.
Ah, okay.
Now, when you use all kind of symmetries, then what you get is the size of the Hilbert space reduced to, for L equal 20 to 369,512. So this is the matrix you are dealing with. Now, for the reason which we wanted to be everything to be number of spin ups and spin downs equal to each other, and number of columns also being large, we used to probe L's that is multiple of 4. Then you can divide it into 1/2 will be empty, 1/4 up and 1/4 down. So next would be 24, and I think Murat was trying to do something with that and got some results, but they're not in my disposal yet. Whether you can go to 28 with his equipment, I strongly doubt. Whether it's possible in principle, I hope yes.
Thank you very much.
Okay, more questions? Yes. Sergey.
Okay. So please, Boris, could you move to some of maybe 3 previous slides where you have plotted the localized and propagating items? Oh yes, this is just what's it is just stage for us to explain what is the extended state and localized state, because here I see the dimension of 2. When as far as I am concerned, the problem is of 1D chain on the shore.
I don't remember. It's a picture with everybody shows, so that I also just took it to emphasize. I have somewhere in my files a picture of 3 dimensions, but taken like 30 years ago, which is now, of course, is finally even to local. I think for Anderson model, at that time, people did wave functions of 100 by 100 by 100. Now I think you can go much further. And I saw pictures in 3 dimensions like that. So here, I believe it's something like a cart or whatever. I don't know exactly about this picture. It's
so this is not about the present problem.
No. It's about Anderson model, but
This is education. This is education. Okay, more questions, please. Yes, Dario.
I mean, the Hamiltonian that you write, somehow it looks a bit similar to the PXP model, the one that has scarce states and so on, in the sense that you have to project zones and then. So I was wondering, when you are in the ergodic regime, can you find some scarce states also there? Some many
maybe, but we were not looking for that. I mean, as I told, this project under the development.
Okay. More questions? Alexei?
Yeah, well, would there be any difference if you go from speed 1 up to speed 1?
Yes, I think it could be a difference, although if you equal to infinity, then only your patterns will be more complicated.
So there will be quantitative or not quantitative?
No, I think you will not have advantages numerically. So your system will be even smaller, and so usually.
Yeah. So I guess it doesn't make sense to do the spinless fermions, because then you don't have confidence. I mean, take the spinless fermions seriously.
No, spinless fermions will give you just 3 gas and columns, and that's
Boris, can you show again these curves at the very, which you showed at the very end, the numerical data with the L equals 10? Right. So what is the ratio of the spin ups and the spin downs here?
I think all of what Moran did was the same spin up and spin down.
Because if you now use this ratio as another parameter, you could go back to the case where
right. But you see, what we wanted at that stage was to compare situation with different L, and that's why comparing L20 with L18 would be maybe not fair, because the occupations will be not proportional to each other. So we wanted to increase all and up and down and L proportionally, so that.
Okay. Yes, please.
So in the case of the constant magnetic field, can you solve that? Constant magnetic field?
Yeah. No, constant magnetic field will just add to the energy and up minus and down times this constant field, and that's it. Because if magnetic field is not changed from side to side, it just adds to the total energy, and you can forget about it.
Will not break into the.
Yeah. No, it will do nothing. It will just even don't change anything.
Sergey, one more question on the back. One more question. Oh, one. We have to finish.
But we can. I mean, I'm not.
Boris is still here. Boris is still here for some days or weeks.
Other periodic boundary conditions crucial for
this
story.
Yes, if you have open boundary conditions, then columns are indeed free, and there is nothing in it.
I think that this boundary condition, this cutting, in fact, cutting the swing, is the type of realization of disorder. Very strong, but very special, but still it can be simulated like this. I believe.
Yes, and I do believe that if you have strong disorder, then states are so localized that if you go, that idea of going around is so improbable that you can forget about this splitting independence of everything on phi, on the plasma momentum of the particle. However, how big is this disorder and how it scales with the system size is still not very clear to me. But if your occupation is not small, then wave functions of the columns get overlapped, and altogether they can make the way around even without moving some particular guy around. I mean, you saw this example of balls on the needles when one is falling and then the last is going up and the rest stays. So something like that could be even if states are localized. If there are many.
Last question.
Second.
Last question. Anyone else? Okay. Sorry, Sergey. No, we have to give other questions. Please.
What's special about the magnetic when rather than the scale?
I told that
when I saw the I mean,
a little bit louder. I'm just really very good at hearing.
So I'm wondering what is special for the magnetic rather than the scalar one?
No, special is that for scalar, for potential disorder, every sequence has the same energy. That's why the pattern has plasma momentum, and this plasma momentum is conserved. It's quantum number. And because it's conserved, then one particle states are indeed one particle state. They don't mix. They just are determined by this. But if they are momentum is not conserved, you get possibility of changing this momentum and simultaneous changing of the column of state. So you change momentum and columns jumps from one localized state to another. And this is not allowed in the case of.
Okay, I think we should stop here and be merciful to our speaker who had a tough job. He was standing for 1.5 hours while we were sitting. And again, Boris is still here with us for a couple of weeks until definitely the end of DDAP 12. So please use the chance and talk to him and discuss. So let's thank again to our speaker. Thanks for And thanks to the organizational team, it was quite a going wrong and break and what happened to this? Oh. But what happened to it? It was just going wrong. Oh my God, just the battery, just the engine.
Of the laptop.
No, I was afraid that my computer is.
No, I just wanted to check it.
For the other systems or only for?
Yes, I did.
Ah,
Actually, for RRG, the KL1 shows transition, but it has also strong finites. I will add it into the same
I just
overlay.
remember, because I think it's good to show it together with.
But actually, for RRG, the ergodic transition it doesn't show.
Oh.
So it's like they overlap. So they completely overlap. And then they start separating, but I don't see, because usually one would have like something like this, and I don't see they're on top of each other. Yes.